This is Module 10, Section 5.2. In this section, we're going to look at negative exponents, more on simplifying exponential expressions, and scientific notation. Let's look at negative exponents to start. The definition for simplifying negative exponents is if you have a base that's raised to a negative exponent, like a to the negative n power, that's equivalent to taking that same exponential expression, taking the reciprocal, and then changing the negative exponent to a positive exponent. So, for example, let's say that you are asked to simplify x to the negative 2 power. Okay? According to the above definition, you can take that base and corresponding negative exponent, take the reciprocal. Now remember, reciprocal simply means you're going to take a fraction and flip it over. Okay? So what's going to happen if you take x to the minus 2, which can be made into a fraction by putting it over 1, as always. If you flip that around, or flip it over, you're going to get 1 over x. Now once you take the reciprocal, that negative exponent becomes a positive exponent. So x to the minus 2 is equivalent to 1 over x to the positive 2. Let's actually put a number in there and see how that works. If you had a 3 to the negative 2 power, okay, if you want to make that into a fraction, you can. That's equivalent to taking the reciprocal, so flipping it over. Now you've got 1 divided by 3, but once you take the reciprocal, instead of being a negative 2, it's now a positive 2. Now that can be further simplified. Okay? 1 divided by 3 squared is the same as 1 divided by 3 times 3, which of course in simplified form is 1/9. All right? Let's look at this example. Let's say you're asked to simplify 3x to the negative 4th. Now you can't forget all of the things you learned prior to this section. Remember, exponents only apply to what is directly to the left of them. So that negative 4 power does not apply to the 3, only to the x. So when you are changing that negative exponent to a positive exponent, the 3 does not move. You don't take the reciprocal of the 3. Only the x to the negative 4th terms moves down into the denominator. And so that negative 4 then becomes a positive 4, and your simplified answer is 3 divided by x to the 4th. Let's say you had this problem. A to the minus 2 over b cubed. Now, note that taking reciprocals really means if a term is originally in the numerator, when you take the reciprocal of it, it shifts down into the denominator, and vice versa. If you have something in the denominator that's a negative exponent, and you want to make it into a positive exponent, if you take the reciprocal of it, something in the denominator comes up in the numerator. So really what you're doing for these problems that are more than just one exponential term is you are moving around the negative exponents either into the denominator or up into the numerator and then changing the sign. So in this case, the negative exponent only applies for the a base. So you're going to pull the a down, take the reciprocal of it. That'll give you now a to the positive 2. If there's already something down in the denominator, what you moved down will simply multiply onto what's already there. And if nothing else is left in the numerator or denominator after you take care of your negative exponent, then there will always be an understood 1. So the simplified answer of a to the negative 2 divided by b cubed is 1 divided by a squared b cubed. All right, let's look at this example. C to the negative 4th divided by d to the negative 5th. All right, here, both of these bases have negative exponents applied to them. So we're going to make those into positive exponents by taking the reciprocal. Again, taking the reciprocal just means shuffling them around in the fraction. So we're going to pull the c base down into the denominator, and we're going to pull the d base up into the numerator. That's going to give us now d up in the numerator to the positive 5 power, because the sign changes to positive once you take the reciprocal. And down in our denominator, the d is gone, but the c has been moved down. And so we've got a positive 4 in the denominator for a final simplified answer of d to the 5th divided by c to the 4th. All right, let's look at this example. A to the negative 3rd times a to the 5th. Now, there's a couple of ways you can approach this problem. One is, if you want to, you can simplify this problem just like we were. We're going to take that term that has the negative exponent applied to it and shuffle it down first. That's fine. So now you've got a to the 5th divided by a to the positive 3. And then you could take that and use properties of exponents that we learned in the previous section. If you have like bases that are being divided, you can write that as a single term by subtracting the exponents, numerator minus denominator, and that would give you a squared as your final simplified answer. Another way you could approach that same problem, and I'm just going to rewrite it here, is, again, using the previous section, if you have like bases being multiplied, you can combine that into a single base expression by adding your exponents. Here, negative 3 plus 5 does give you a squared. Same answer, slightly easier in that problem. So notice that negative exponents follow properties of exponents just like any other exponent. Okay? Let's do one more example. If we've got b to the negative 8th times b to the 6th, all right, again, you could, if you wanted to, change that b to the negative 8th into a b to the positive 8th by pulling it down into the denominator. I'm going to choose, though, to apply properties of exponents first. So I'm going to add my exponents. That's going to give me then b to the minus 2 power. Now the rule in math is you never leave your final answer with a negative exponent. So this is not considered good form. You have to take it that extra step. You need to pull that down into the denominator, take the reciprocal, to get a simplified answer with a positive exponent, and that would be your final answer for that problem. All right, so let's look at some more complicated problems using what you now know about negative exponents and all of the property of exponents that you learned about in the previous section. So let's say, for example, I wanted you to simplify x to the 12th times x to the negative 7th divided by x cubed times x to the 4th. Okay, several different ways you could do this problem. I'm going to choose to simplify the numerator and then simplify the denominator using property of exponents. So like bases being multiplied can be simplified by adding the exponents. So I'm going to do that both in my numerator and my denominator. That's going to leave me with 12 plus negative 7 is the same as 12 minus 7, and that's x to the 5th. Down in the denominator, x to the 3 plus 4 power is x to the 7th. Okay, now at this point, I can rewrite that base by subtracting numerator minus denominator. And that's going to give us x to the 5 minus 7 is negative 2. And that gives us 1 over x squared. Okay, let's look at another example. Let's look at this example. Let's say we have negative 15 r to the negative 6s divided by 5 r to the negative 4th s to the negative 3rd. All right, we're trying to simplify. So we are going to approach this problem in a couple of different ways. One is to take it just as written and use properties of exponents. Okay, let's start with a constant since we don't need properties of exponents to simplify that. If you look at 5 and 15, you agree with me that there's a common factor of 5. So if you divide 5 out of both your numerator and denominator, 5 divided by 5 leaves you with 1. Negative 15 divided by 5 leaves you with negative 3. All right, now you have some like bases here. So if you want to use properties of exponents before you move your negative exponents up to be positive exponents, you can. Or you can move the negative exponents either up or down, depending, to make them positive exponents first. It's up to you. I'm going to choose to use the property of exponents first. So I've got negative 3 up in the numerator. I'm going to combine my base r's by subtracting my numerator minus my denominator. In both cases, for r and s, remember s has an understood exponent of 1, so we've got 1 minus negative 3. Now all that is in the numerator. When you use the property where you subtract exponents, that remaining base always is up in the numerator. Therefore, notice that the only thing left in our denominator is a 1, and so we can ignore that denominator now. So now we've got negative 3. R to the negative 6 minus negative 4 is the same as adding a negative. So negative 6 plus 4 is negative 2. We've got s to the 1 minus negative 3 is the same as adding a positive. So that gives us s to the 4th. Okay, and again, that's all over 1, and I put that 1 back in because I can see that to get my final answer, I'm going to have to move my base r down to the denominator. So we've got negative 3 s to the 4th divided by, sorry, that's not an s, r to the positive 2. And that's your final answer. You cannot combine the s and the r because they're not like bases, and therefore you cannot combine them. All right, let's look at one more example. Let's look at this example. A to the 6th, b to the minus 2, all raised to the 4th power, divided by the group 4a to the minus 3, b to the minus 3, raised to the 3rd power. Okay? Let's get rid of those groupings by distributing that power. Remember, it's not really distribution, but we're calling it that because it looks very similar to distribution. We're splitting the power out to each term. So we've got a to the 6th, and we're applying that 2nd power of 4 to it, times b to the, let's see, what was that? That was a negative 2 raised to the 4, divided by 4 cubed. We're splitting out that power of 3 on the outside, times a to the negative 3rd cubed, times b to the negative 3rd cubed. All right, powers to powers multiply, so let's do that. We've now got a to the 24th, b to the negative 8th, divided by 4 cubed. 4 times 4 is 16, times another 4 is 64. And we've got a to the minus 3 times 3 is negative 9th. B to the minus 3 times 3 also is negative 9th. All right. Now we can combine our a's and our b's there, or we can move our negative exponents into positive exponents if we want to do that instead. Totally up to you. Okay, so we've got here a 64 down in the denominator. And if you're using the property of exponents where you're subtracting 24 minus a negative 9, remember we said that subtraction step always, at least temporarily, puts things up in the numerator. So we've got like base a's, and we subtract 24 minus a negative 9. We've also got like base b's, so we've got b minus 8 minus negative 9. Now we've got, if we clean that up, a to the 24 minus negative 9 is the same as adding a positive. So we've got a to the 33rd. We've got b to the negative 8 minus a negative is the same as plus a positive. So b to the negative 8 plus 9 leaves us with b to the first divided by 64. Nothing more we can do there. So that would be our final answer. All right, let's look at some more examples then. Let's look at this example. Let's say we have 5 to the negative 1 power times z to the 7th power divided by 5 to the negative 2 power z to the 9th. All right, we have like bases, so let's look at this, and we'll use our property of exponents. Those are like bases, so to combine them, we're going to subtract numerator minus denominator. Okay, same thing is true with our z's, so we've got z to the 7 minus 9. That's going to give us 5 to the minus a negative is the same as adding. So we've really got negative 1 plus 2. Negative 1 plus 2 is a positive 1. Z to the 7 minus 9 is negative 2. Now we can't leave our final answer like that because negative exponents in a final answer are not allowed. So now we've got 5 in our numerator, and we've got z to the positive 2 in our denominator. Let's stick with that same problem a minute, and let's go ahead and solve it another way to make sure we get the same answer. Let's say that we decided that we wanted to get rid of negative exponents first. So we decided to move those two negative exponent terms around to make the negative exponents positive. That would give us, for this problem, we moved the 5 to the negative 2 up, so now we've got 5 to the positive 2 up top, along with the z to the 7th, which we didn't have to move because it was a positive exponent already. We moved the 5 to the first down, and we still have the z to the 9th. Now if we use properties of exponents, we've got base 5 to the 2 minus 1 power times z to the 7 minus 9 power. That gives us 5 to the first, z to the minus 2, and then as your final step, you still need to move that z down, and we get 5 over z squared. Same answer, approached a little bit differently, but same answer in the end. Okay, let's look at this problem. Let's say I asked you to simplify the quantity negative 3 x squared y squared all raised to the negative 2 power divided by the quantity x, y, z, that quantity also raised to the negative 2 power. Okay, when faced with a situation like this, it almost always is easiest to distribute that power first, especially when inside the groups all the bases are different, so there's really nothing you can simplify inside the groups. So get everything out from that group before you try to shuffle things around. So now you've got negative 3 raised to the negative 2 power times x squared raised to the negative 2 power times y squared raised to the negative 2 power, all divided by x to the negative 2 times y to the negative 2 times z to the negative 2. Okay, let's clean up the power to power steps. Those are multiplication steps. So you've got negative 3. And let me back up just for a minute. Because that negative 2 power in the numerator is being applied to both the negative and the 3, I should have put parentheses around that negative 3 to indicate the power of -2 does go for both the negative and the 3. To write it the other way, we talked about this in an earlier section, is actually incorrect. Because if you write it without the parentheses, then the -2 would only apply to the 3, not the negative. So I'm going to fix that. I do need parentheses around the -3. Okay? And now we're going to clean those powers up. 2 times -2 is -4. Powers to powers multiply. Y to the 2 times -2 again is -4. And that's all divided by x to the -2, y to the -2, z to the -2. Okay, now at this point, there's a couple of different ways you can approach this. You could notice that there are like bases that are being divided. So you could subtract exponents, which is the way I'm going to approach it. Or if you'd rather shuffle those terms around to make all those negative exponents positive by taking the reciprocal, you could also do that. That's totally up to you. I'm going to choose to use the properties of exponents next. So if you're using subtraction to combine that x to the -4 and x to the -2 into a single term, remember it's up in the numerator when you do that. So you've got -4 minus a -2 for your x's. Your y's, you're going to have -4 minus a -2. And then down in your denominator, you still have that z to the -2, which you haven't been able to combine with anything else yet. All right, so let's do that subtraction. We've got -3 to the -2 times x to the -4 minus a negative is the same as adding 2. So -4 plus 2 leaves you with -2. Y, same numbers, so you're going to get the same value there, divided by z to the -2. All right, now I have all different bases there, so I'm going to choose now to get rid of all of my negative exponents. So I'm going to shuffle the negative exponents in the numerator down and shuffle the negative exponent that's in the denominator up. So that leaves me with z to the +2 in the numerator because I pulled it up. And I've got -3 to the +2 in the denominator. I've got x to the +2 in the denominator. I've got y to the +2 in the denominator. Okay, so now I've got z squared divided by -3 squared. -3 times -3 is a +9. X squared, y squared. Those are all different bases. There's nothing more I can do. That is my final answer for that problem. Okay, so we're going to move on to a new topic, scientific notation. In science, we often have to deal with either very large or very small numbers. For example, light travels approximately, oh gosh, let's see, that would be thousands, millions, billions, trillions, I guess. 5,880,000,000,000 miles in 1 year, which is 1 light year. A very large number, you would agree. Another example is the mass of an E. coli cell, which is 0.000000000000000004 grams. It is difficult to do calculations with these numbers in standard notation because of the large number of zeros involved with them. Scientific notation allows us to express and manipulate these numbers in a more manageable form. So for the above examples, okay, the speed of light there, which is written in standard form, to your left, looks like this in scientific notation, 5.88 times 10 to the 12th. Okay? It's the same number, it's just written differently. But you would agree that it's much easier to write it in scientific notation in terms of writing than the original standard form that we introduced it in. Same thing is true with the weight of that E. coli cell. There's just an unmanageable number of zeros in front of that 4, but written in scientific notation, that number is 4 times 10 to the -16th. much easier to write, and once you understand scientific notation, much easier to understand as well. All right, so the question then becomes, well, how do you convert back and forth between those two forms? So I'm going to give you a step-by-step method to convert in both directions. If you already know a method that you were taught in a previous class, you don't have to use my method. Certainly, if you've never seen it, though, this method is pretty slick and works pretty easy. So to convert from standard form, which is what you're used to seeing, to scientific notation, here are the steps that we're going to do. You're going to place the decimal point after the first non-zero number as you look at the number left to right, and you're going to multiply by some power of 10. To find the exponent for the 10, you're going to count from step 1 how many decimal places you need to move to get back to where the decimal point was in the original decimal form. Decimal form and standard form are the same. This will be your exponent. The sign of the exponent is positive if you moved right to get back to the original number, and negative if you had to move left. So let's look at some examples. In standard form, let's look at the number 79.32. To convert that to scientific notation, look at the number left to right and put the decimal after the first non-zero number and carry the other numbers along. So looking left to right, you agree the first non-zero number is 7. So we place the decimal after the 7, and we know that's going to be multiplied by some power of 10. All right, so we put the 10 in. Now we have to figure out what the exponent is and what the sign of the exponent is. So take the decimal place where you put it, we put it here, and figure out how many places you'd have to move that to get it back to where it originally was in standard form. Do you agree with me that you'd have to move one place and you'd have to move right to get it back to where it originally was? One right, in terms of scientific notation, means positive 1. Positive is right, negative is left. And to check that, if you take 7.932 and multiply it by 10, you do get 79.32. It's the same number, just written differently. All right, let's look at this number. Let's look at 65,789. To write that in scientific notation, look at it left to right, put the decimal point after the first non-zero number you come to. Write all of the other numbers in the problem, and then multiply that by some multiple of 10. Okay? Now, you place the number after the 6. The number originally was at the end of the number. If a decimal point isn't written, it's understood to be at the end of the number. So to get it back to where it originally was, you'd have to move 1, 2, 3, 4 places. And again, you moved right to get it back to where it originally was. That means in terms of exponent, positive 4. And again, if you put that in your calculator, 6.5789 times 10 to the 4th is going to give you 65,789. Let's look at this problem. 0.0093. Okay. Looking at that number left to right, the first non-zero number is the 9. So we're going to place the decimal after the 9 and multiply it by some power of 10. Okay. We placed the decimal after the 9. It originally was over here in between those zeros. To get it back to where it originally was, we'd have to move 1, 2, 3 places. And we moved left. That means a negative 3 in terms of exponent work. Okay. Now, what if you're going in the opposite direction? What if you're converting from scientific notation to standard form? What you're going to do is look at the exponent and move the decimal point as follows. you're going to move right the same number of places as a positive exponent indicates, and left the same number of places as a negative number indicates to get it back to a number in standard form. So this is even easier than converting into scientific notation. Let me give you some examples. Let's say I gave you this, 8.03 times 10 to the fifth, and I asked you to convert that to standard form. Okay, it's all in the exponent. What you're going to do is you're going to take the value as written, and in this case, since you have an exponent of positive 5, that means in terms of decimal point movement, 5 places to the right. Positive means right, negative means left, just like in the conversion to scientific notation. So take that decimal point and move it 5 to the right. You may need to put in placeholder zeros in order to do that. So we're going to move 1 place, 2 places. We run out of numbers, so we have to put in placeholder zeros. That's 3 places, 4 places, and 5 places. We're going to put the decimal point right there. And so let's rewrite that so it's not quite as sloppy. We've got 803,000. Okay, the decimal points at the end of that, that would be the same as 803,000. All right, let's look at this number. 1.23 times 10 to the negative third. To convert to standard form, you're going to take the number as written. We've got 1.23. We're going to look at the exponent. Okay, negative 3 means 3 to the left. So take that decimal point, move it 3 to the left. So 1 to the left puts it before the 1. We're going to have to put in some zeros. 2 to the left, 3 to the left, we'll put it right there. And to clean that up then, our decimal point is 0.00123 in standard form. Therefore, 1.23 times 10 to the negative third is the same as 0.00123. Okay, so let's do a few more examples. Let's say you are asked to convert the following to scientific notation. These are your problems here. We've got 4,300,000,000. Okay, I want you to convert that to scientific notation. So working left to right, put the decimal after the first non-zero number. Now, if everything else is trailing zeros, you do not need to write all those. You can drop those zeros, multiply that by some multiple of 10. To figure out what multiple of 10, look at the problem, figure out where you put the decimal, which was after the 4, and where it originally was, which in this case is at the end of the number, and figure out, to get it back to where it originally was, how many places would you have to move, and in what direction. So we would have to move, to get it back to where it originally was, 1, 2, 3, 4, 5, 6, 7, 8, 9 places to the right, which means a positive 9 exponent. 4.3 times 10 to the 9th is the same as that original number in standard form. Okay, let's look at this. 0.000018. Write that in scientific notation. Looking left to right, put the decimal after the first non-zero number, and you know that's going to be multiplied by some multiple of 10. All right, go back to the original number. We placed it after the 1, but it originally was way over here to the left in the midst of all those zeros. To get it back to where it originally was, we're going to move 1, 2, 3, 4, 5, 6 places to the left. 6 left means negative 6 in terms of exponents in scientific notation. All right, let's convert some from scientific notation to standard notation. Let's look at 8.403 times 10 to the fourth. Okay, it's all in the exponent. Look at the exponent. Positive 4 means in terms of decimal movement 4 to the right. So take the problem, move it 4 to the right, putting in placeholder zeros if necessary. Okay? So as we move 4 to the right, we go 1, 2, 3. We are going to have to put in a 0. The decimal point is now going to be at the end of that last 0. So we've got 84030, and put in a comma if you want, 84,030. All right, let's convert 4.3 times 10 to the negative 6. Look at that exponent. Negative 6 in terms of decimal movement means we're going to go 6 left. Negative means left. So take the original problem, put in zeros as needed. To move 6 to the left, we're going to move 1 to get in front of the 4, 2, 3, 4, 5, and 6. So in standard notation, we've got point, and we've got 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros, 4, 3. So 0.000043 is equivalent to 4.3 times 10 to the negative 6. That brings us to the end of Module 10, Section 5.2. You should now complete the homework for Section 5.2 found in MyMathLab, and when you have successfully completed that homework, proceed to the video for Module 10, Section 5.3.